Hi. So today I'm going to start another subject, theory of automata and formal language. In the reputed college like IITs and NITs, this course is usually taught with the name theory of computations. Okay, so in this video I will talk about the introduction, what we are going to see in this course, the history, the basic definitions, the basic other things so that are very useful for this course. Okay, so let's begin. So in the overview, this is the overview. These things we will see in the further videos. So we will talk about the DFA, NFA, epsilon NFA. These are basically finite machines without output. So these are also called as the language acceptors. So you will see the Moore machine, Mealy machines. Moore and Mealy machines are the finite automata with output, and these are also called as the language transducers. Okay. So difference between acceptor and the transducer is that acceptor usually accept the string or reject the string, and transducer will give you the output corresponding to your input. Okay. So how the language is constructed? So we will have the regular language, we will have context-free language, context-sensitive language, recursive and recursively enumerable language in this course. Okay. So we will also have the automata, various machines corresponding to these language. So like regular language is accepted by finite automata, context-free language will be accepted by the push-down automata. Similarly, recursive and recursively enumerable language will be accepted by the Turing machines. So we will talk all of these things. Okay, fine, no problem. So let's begin with the introduction to automata. So what is automata? So you can see that this is a block diagram in which you can easily see the various input here. So these are the input, and you are giving the input to this block, and I am name them automaton. Okay, so automaton is a singular word for automata, right? So this automata will compute something. It will have some state like q1, q2, q3 up to qn. So it will take some input and it will give me some output, right? So this is the basic diagram, diagram for or basic model for automata. Okay, so automata is usually process the discrete informations. Okay, so in this course we will talk about the automata which will take only the discrete information. It will not take the continuous informations. Okay, so no problem, I think. So automata is a singular word for automata, and if you talk about the definition of automata, you can say that it is a mathematical model which will take some input and it will process that input with the help of various states, and then it will give us the output. Okay, so you can also see that automata is the study of abstract computing device or the machine. So let's begin with the history. So this story is actually automata story is started in the back 1930 with the studies of Alan Turing. Alan Turing was a computer scientist. He proposed a machine, and he said that there is a machine which can done, or which has capability of today's computer. What the today computer can do, that machine can do. Okay, so he named that machine the Turing machine. So Turing machine can have the capabilities of today's computer. Whatever today's computer can do, the Turing machine can perform. Okay, so Alan Turing goal was to explain what is these computing machine can do, and what the things it cannot do. Okay, so there can be a solvable problem and there can be a non-solvable problem. Solvable problem are those problems the computer can do or the Turing machine can do, and non-solvable problem are those solvable which will not be solved by the Turing machines. Okay, so in 1940 to 50, so there is a study comes into the existence, finite automata, and initially the finite automata was originally proposed to model the functioning of brain. Okay, so let's say brain takes some input and it gives some response, output in the form of response. Okay, so in 1950 there is a scientist called Chomsky, and he studies the formal grammars. Okay, so basically the grammar have close relationship to the abstract automata, you can relate the grammar with the language and then language to the automata. So language is basically the inputs to the automata, and you can use those things like grammar in the compiler design. In the compiler design, like you want to design the C compiler, you want to design the Python, you want to design the Java compiler, so you can use these formal language in the study of the compiler design. Okay. So in 1969, there was a scientist called Cook, and he separated the solvable problem from non-solvable problem. Okay, so your non-solvable problem are basically he said that these non-solvable problem are basically solvable problem, but it will take the huge time to solve. Okay, it will take the huge time to solve, and these problems are usually called as the intractable problem, or not traceable problem, or you can also you can also say that these problems are also called as the NP hard problem. So in the end of the course, before the end of this course, we will talk about the NP hard problem, we will talk about the NP complete problem. Okay, right. So now why we study this course? So motivation. So this finite automata is actually, you can model any software as well as the hardware. So basically, before the actual design of any software or hardware, you can design the mathematical model, and mathematical model will be provided by your automata. Okay, so you can check that, you can design and you can check the behavior of the digital circuit before the actual design. Okay, so you can also use the mathematical model or the automata in the lexical phase analysis of compiler design is actually fine. And sometime you search something on the Wave or in Google, so you write something, let's say you want to search the example for the finite automata, so you just write finite automata example. So this finite and then automata and then example keyword is usually mapped with the web pages. So the application of this finite automata or the automata is used in pattern matching on the Wave. Okay, so you can also verify a system, a small system or the large system using using finite number of states. So this is actually the motivation behind this course. So you can actually model any software or any hardware before the actual design. So this is the main motivation behind this course. So why that's why we are studying this course. Okay, so no problem. So let's begin with the simple machine. So I'm going to tell you the on off switch. So this is the activity you have already performed in your high school. So what do you do in this activity? So there is a bulb connected with the circuit and there is a switch, and this switch is also connected to a battery which will glow this bulb. So whenever you push this, whenever you close this switch, that means the bulb will glow. Whenever you open this switch, the bulb will not glow. Similarly, so state of these two bulbs is either off or on. Okay, so you can have two state, and I am representing the state with the help of a single circle. Okay, a circle. So this is my off state and this is my on state. Fine. So there will be a starting state. So initially bulb was in off state. Okay, so usually the starting state is represented by circle and the arrow sign. Okay, circle and the arrow sign. So this is your starting state, and generally the state is represented by the single circle. Okay, fine. So whenever you push the switch, whenever you close the switch, the bulb will on, and whenever you again push the switch, the bulb will be off. So this is a very simple activity corresponding to the on off switch, and you can relate this problem with your household switch also. Okay, so now let's see another example. So you want to recognize then, suppose that you want to design a compiler for your a particular language, let's say C, and there is a keyword, let's say then, and you want to recognize whether then is accepted by your automata or not. So you will start from your starting state. So this is your starting state, and how to know what is the starting state. So starting state is represented by single circle and this sign. Okay, so these are intermediate state in the intermediate states, and the final state is usually represented by the two concentric circles. So this will be your final state. Fine. So now you already know how to know which state. So this is your starting state, these are intermediate state, and this is final state. Fine, no problem. So you want to recognize this then keyword. Okay, then word. Okay, first you will read this t from this. Okay, so this is the input to this state, so you will read t, and whenever you read t you will reach to the next state. Okay, the name of this stage is nothing, and name of this stage is, let's say, t. So this is telling me that you have already read the t. Now from this state your next input is h, so you will read h and then you will reach to this state. So this state is indicating that you have already read the t and h, th, and then you will read e. E is your next input. After reading e you will reach to the next state, which is indicating you have already read the, and then you will read n. So then is complete, your input is finished. So you want to recognize the then, so you will reach to the final state after accepting the then. Okay, so we will discuss more example in the next videos. So state are usually represented by the circle, and for a given input and the state, so there will be a transition. So these are the transition corresponding to this state. Let's say the state name of this state is, let's say, q0. So from q0, from this state you have input. From q0 you have input t. Okay, so you will reach to which state. So this is a transition for state and the transition, so you will reach to the same or another state. So here in this case you are reaching to the next state. Okay, fine. So you will have a starting state from which your machine will start, and there may be one or more than one final state in your automata. So these are the two very simple example for you. So what are the representation and the issue? So usually your language is actually construct with the help of your grammar. Okay, and you can also have the regular expressions and other grammars. Grammar is present for every, you have a regular language, so you will have a regular grammar for the regular language, regular grammar for the regular language. And suppose that you have context free language, you will have context free grammar for that. And similarly you will have context sensitive grammar for context sensitive language. So there will be a grammar for present for the every language. Okay, so you can also have the expression by which you can represent your languages. Okay, now what are the issues? So first issue is what computer cannot do. So there are several problems. So we have problems, so we want to solve the problem. So problem can be solved by the computer and it can not be solved by the problem. So you can divide the problem into two parts: solvable problem and unsolvable problem, right? Unsolvable problem. So whenever you able to decide whether the problem is solvable, so this is the problem related to the decidability. You are able to decide the problem is solved. Okay, and there can be the non-solvable problem, which can be considered the undecidable problem. Okay, similarly the problem is solvable, so your next focus is on the efficiency, whether this your solution is efficient or not. It is taking less complexity. So this is considered to be as interactability. So computer can do, and my focus on the efficiency. Okay, so the solution should be less complex, produce the less complexity. So it should be problem should be decidable and it should be interactable, so that the work can be do in the efficient manner. Okay, so now the basic things which we will use in almost every next videos. So how to design a language. So basically for designing a language, so language will consist of basically the string, and string are formed using the alphabet. So you can relate this problem with the help of your English language. So English language have some alphabet like A, B, C, D up to Z. Okay, so with the help of this A, B, C, D, so you may design some string, like you want to write let's say book B double O K. So in this we are using B O and then K. So this is your string. And if you talk about the English language, so English language is a collection of all the possible word over the alphabet. So alphabet is nothing but a finite non-empty set of symbols. Okay. So usually if you write A comma B comma C, so these are the symbols. Okay. So if you put them into the set like A B C, so in the high school class you have understood that your set is represented by the curly braces. So if you put these symbol into the curly braces, it will become set. So your alphabet is represented by sigma, and it is a finite non-empty set of symbols. So these are the symbol and this is the set, and set is represented by the curly braces. So you will put all these things in within the curly braces, right? So sigma is equal to here 0 comma 1, which are the binary alphabet. So 0 and 1 are the symbols, and if you put them into the curly braces, it will become your alphabet. Similarly, alphanumeric numbers A to Z, A to capital letter, small letter, and then the digital the decimal number. Okay. So now you have understand that what is alphabet. So alphabet is consist of the symbol. So it is a finite non-empty set of symbol, and symbol is also called as the basic building block. So the definition of symbol is basic building block. So symbol is your basic building block which will be used to construct the alphabet. Fine, no problem. So now how these string will be formed with the help of alphabet. Okay, so a string is also called as the words. So it is a finite sequence of symbols taken from sigma. So you have sigma, this is your sigma given to you, and how to construct the various string, like you can use the 0 and 1 together, so it will become 0 1. So 0 1 is our string which will be construct from these input alphabets. Okay, so you can use the 0 0 2 time and then 1 and then 0. So this is also a string, okay, made up by these symbols. Okay, similarly if you have alphanumeric numbers, so you can like design TOC123 CS2020. So these are also a string over this sigma. Okay, sigma is alphabet. Sigma is a sign to represent the alphabet. So in the automata you also have a special string which is called as the empty string, and it is usually represented by epsilon, and the meaning of this empty string is zero length string. So this epsilon is usually called as the string of length 0. Okay, so if you talk about the length of a string, so suppose that this is a string 011 so the length of a string is usually represented by the, suppose that W is a string, so W mod. Okay, so W mod is here equal to 6, 1 2 3 4 5 6. Similarly here you can also count the length of this W. So here you can see that the length of the length of the empty string is 0. So 1 2 3 4 5 6 7. So here you will have the length of W will be equal to 7, and similarly the length of epsilon is 0. So this is a special string which is also called as the empty string epsilon. It is usually represented by the epsilon, and you can also name it null string. Okay, so the advantage of a string is that whenever you want to read nothing and you want to stay in the same state, so you can then use this string. Okay, fine. So now before the language, so before, let's say this symbol construct the alphabet, and alphabet construct the string, and collection of a string is called as the language. So before the language, let's talk about the power of any alphabet. So suppose your alphabet is usually represented by sigma. So if you have power to this alphabet, so it is represented by sigma to the power k, and it is called as the length of string k. Okay, suppose that there is a given the given sigma is equal to a comma b. So you want to find the sigma to the power 0. Okay, so your sigma to the power 0 is usually called as the string of length 0, and you have just know that string of length 0 is your epsilon. Okay, And similarly you can count the sigma to the power 1, which is called as the string of length 1. Okay, so from the sigma, so this is your sigma, and from the sigma you can write the string of length 1. So a is a string of length 1, b is a string of length 1. So these are the two possible string of length 1. Okay, but you can here you can see that the sigma to the power 1 is equal to the sigma, but there is a difference between these two. Sigma to the power 1 is the string and this is your alphabet. Okay, so this is the difference to note, so keep remember it. So this is your string and string of length 1, and this is the alphabet. Okay, so that is the difference between these two. These two are not technically equal. Sigma to the power 1 is not equal to the sigma. Similarly you can count the sigma to the power 2, which is also called as the string of length 2, string of length 2. And if you have sigma a comma b, so you can write a b b a b b. Okay, so it can perform with the ordered set of a comma b cross a comma b, a and then a b and then b a and then b b. So here you can write like this. Similarly you can also count the sigma to the power 3. So sigma to the power 3 will contain all those strings of length 3. So a string of length 3 can be written like this: a b a and so on. Okay, similarly you can write the sigma to the power 4, sigma to the power 5, sigma to the power 6 and so on, sigma to the power n. Okay, so there is a special sigma to the power, let's say, star. So star means collection of all these strings, collection of all these strings from sigma to the power 0 to sigma to the power n. Okay, so this is the collection of all the possible string over alphabet. So whatever with the possible string, so sigma star will contain all those strings. So sigma to the power sigma star is usually contain the length of string 0, length of string 1, length of string 2, and then length of string 3, length of string 4 up to n. Okay, you can also write like this: this is the sigma to the power 0, sigma to the power 1. So you can write it as sigma star is equal to sigma to the power 0 union sigma to the power 1 union sigma to the power 0, 2 and union and so on. Okay, so there is also a symbol sigma to the power plus. Okay, so this is actually exclude the sigma from the sigma star. So it is let's say sigma plus is equal to sigma star minus sigma. Okay, so or in other term you can write the sigma star equal to sigma plus, here should be union. Okay, this should be union, sigma plus union epsilon. Okay, so I think the power of an alphabet is clear to you. So in the last language, so how can you construct the language? So sigma star is the string collection of all the string possible over sigma. Okay, so you can choose your language from this sigma star. So you can write like this: sigma L is equal to the L is subset of sigma star. So basically your language is a set of string chosen from sigma stars, because sigma star will contain all the things. Suppose that from sigma star, here in this case, so let's say another example. So suppose that you have a sigma equal to 0, 1. Okay, so what will be your sigma star? So sigma star will contain all the string possible over this, like epsilon, and then string of length 1, and then string of length 2. Okay, and then you will have a string of length 3 and so on. So let's say your language is L is your let's say even length string. So I am defining the language as even length string. So what will you write? So you will write this language string of length even length. So in this case you can see that this is the even length string 0 0 0 1 even length string 1 1 even length string 1 0 even length string, and then you will have 0 0 0 0 4 length string, similarly 0 0 0 1. Okay, and then after 4 length string you can have 6 length string, 8 length string, and so on. So this is actually sigma star will contain all the string, and this is the subset, this will be the subset, language will be the subset of sigma star. Okay, so we will choose our language from this sigma star. Fine. So here also you can see some examples: set of string over binary number with same or equal number of 0 and 1s. You can see that this contains 0 number of zeros and 0 number of 1s. Similarly, 1 number of zeros, 1 number of 1s, 1 number of 0, 1 number of 1. Similarly, 2 number of 0, 2 number of 1. So this is a language over sigma star. Similarly, you can have a set of string over binary number sigma 0, 1, string ending with 0, 1. So this is a string ending with 0, 1, ending with 0, 1, ending with 0, 1, and ending with 0, 1. Okay, and the representation will be like sigma star is a language for any alphabet sigma. Okay, and your phi will represent, gives you the empty language. And if you write like this, L is equal to epsilon, so this will be your empty string. The language consists of empty string. Okay, so fine for this video. So I will talk about the DFA. I will start the DFA in the next video. So I have taken the various things from these books, KLB Misra books and the Ullman books. So looking forward for next video. Thank you.